let's talk about equilibrium. When we were together on Thursday, what we addressed was the substance of a chemical reaction that led us to an equilibrium position. And I'll go ahead and give this example of that chemical reaction up front here again today, and we'll keep coming back to this example of a chemical reaction as we go forward. And those of you in the room, I hope this came through well over Zoom when we were together on Thursday, that you saw this brown gas in the container. And that brown gas was NO2. And it was being combined to make this colorless gas N2O4. And the more of the NO2 that reacted to form N2O4, the more colorless the container became. It was pretty brown, the container was at room temperature. When that container was put on ice, we got more of the N2O4 out. We got a much clearer container that resulted. And I determined a free energy for that. Okay? I'm going to go ahead and write this down the way I remember it now so I don't have to come back and remember it later. And that reflected that the formation of this colorless gas was just a tiny bit spontaneous at 298 Kelvin. At room temperature. At the very end of our time today, we'll come back to that delta G value. And we'll see what that delta G value can tell us about the behavior of this gas, this reaction between these two gases. Okay? But I want to use this reaction as an example of the types of stuff that we're going to be dealing with as we get into this mathematics of equilibrium. Okay? Another reason I want to make sure I sound great alarms now is because you're going to find that we're moving into the most heavily mathematical part of the course. A lot of the feedback I got from first assessment was feedback of the sort of, Pearson, this is a lot of equations at this stage of the course. It's a bear to keep them all straight. And it's a bear to recognize which thing goes with which thing. And to that I have good news and bad news. Okay? The good news is it's relatively straightforward to put together equations that deal with the equilibrium in a chemical reaction of this sort. The bad news is that every reaction of this sort has a different expression for the chemical equilibrium, a different equation that you have to recognize how to assemble. And that difficulty in assembling the equations is going to be our primary business here in what we're trying to accomplish. Okay? So let me start to work on the language and make sure we have the language right. What determines equilibrium for a chemical reaction of this sort is a quantity that those of us who do the physical chemistry for a living like to call the activity. And there are better definitions of activity out there, but I want to be as straightforward as possible as I introduce these ideas. And so what I want to talk about as I put together this concept of activity is how accessible that the compound is to participate in the chemical reaction. Now, what phase are both of these compounds in this story? They're both in gas phase. So this is going to be a situation where everything is spread out 9 ways from helter-skelter. And so we like to think that these particular compounds are going to be very accessible because they're spread out and dispersed. And I'll talk about dispersed stories here in a little while. There are 2 dominant ways that we're going to use in these ideal chemical reactions to measure the activity, the accessibility of a compound. And these guys are in the gas phase. And so one way we're going to use to represent this accessibility is going to be pressure. The greater the partial pressure of a particular participant in this reaction, the more accessible that particular compound is. And I'll go ahead and use P subscript NO2, for example, to represent the partial pressure of NO2 in a container. Why do I say partial pressure? Well, there's N2O4 present as well. And I need to talk about the N2O4 present in addition. What's the total pressure in the container equal to? The sum of the partial pressures, the sum of the pressure of the NO2 and the pressure of the N2O4. Now, pressure is one way we can measure activity. It turns out to be a relatively weak way and a relatively difficult to manage way to talk about activity. We'll use it sometimes. It'll pop up in your homework every now and again. But far more frequently than pressure to measure activity, what I'm going to use is concentration as a measure of activity. Now, how does concentration get measured? Deep, dark Gen Chem 1 reminder. How does concentration get measured? we can do concentrations in percentages, and much of your experience can be saying that a particular solution is 5% 5% acetic acid weight by volume. That's a classic rating for vinegar. Okay. But when we actually talk about these things chemically, we very rarely put those concentrations in percentages. We have another unit that we referred to concentrations in when we studied them in Gen Chem 1. Solubility is getting there. Many solubilities are expressed in grams per milliliter or stuff like that, or grams per liter. But we resist using grams when we tell these stories. I heard something on the Zoom, sorry. I thought I heard something on the Zoom, sorry. And this is the awkward thing about having the earbud in, is I have to communicate what I hear on the Zoom to everybody else, and I keep talking through. The chat. Concentration units, molarity. What's molarity? Not grams per liter, but moles per liter. Absolutely. So I'm content with general pressure units over here, maybe in atmospheres, maybe in torr. But concentration units, I'm going to refer to in molarity units, in units of moles per liter. Okay? That doesn't seem like it would work super well for a gas on first blush. But if I'm thinking about a gas, and I'm thinking about the parameters of a gas I would have used with the ideal gas law, well, one of those parameters is moles. And another of those parameters is volume in liters. Moles per liter for a gas turns out to be pretty easy to compute. Now, let me be real particular about how I want concentration units presented and how I want concentration algebraically represented here. We may have used symbols like M or C previously in the first course to represent concentration. Okay, as we get into this course, what I'm going to do to represent the concentration of something like NO2 is write the formula NO2 and then put it in square brackets. This square bracket formulation represents the concentration of NO2 in moles per liter, or in molarity units. You're going to start to see this representation of concentration, a compound written in square brackets. You're going to see this a lot in the days and weeks to come. And every time you see a compound symbol written in square brackets, your immediate response should be, that's the concentration of NO2. That's the number of moles of NO2 per liter of container. Or alternately, that's the number of moles of sodium ions per liter of solution. Okay? I'm not giving you any such summation of the concentration units. Total concentration equals partial concentrations of each stuff. Sometimes those particular summations don't work as neatly as you would like for them to for concentration. So I'm going to leave those alone for a bit. Okay? I'm much more frequently going to be using concentration as my measure of activity than I'm going to be using pressure. And there are a couple of reasons for that I'll get into. Two more definitions. The reaction quotient is a specific ratio of the activities. Let me be plain with the activities. I can write a reaction quotient as a ratio of pressures or as a ratio of concentrations. But a reaction quotient is the ratio of activities of the products to the activities of the reactants in a reversible chemical reaction. Reaction quotient is symbolized, put the pen the right way, by the letter Q. And if I am in the very special circumstance where I have the value of a reaction quotient at chemical equilibrium, I call that quotient the equilibrium constant. And that's represented by a capital K. Let me come back to my example reaction again. You know, this particular way of writing the reaction, it's a little bit too sophisticated for me. I'm going to write it a slightly simpler way. Tell me if you agree with me how I write it. You agree that's the same reaction as the reaction I wrote above it? The reaction quotient for this reaction is a ratio of activities of products to reactants. Let me write a concentration reaction quotient for this reaction. Concentration Q And that'll be the concentration of the products over the concentrations of the reactants. Okay? And for every instance of product, I write down the formula of that product in brackets. And for every instance of that reactant, I write down the formula of the reactant in brackets. Of course, algebraically, it's just a little bit silly for me to write down concentration of NO2 times the concentration of NO2. And I can simplify that down, right? If this was x times x in the denominator, how would I simplify x times x down? X times x? How do I simplify x times x? What can I do to very straightforwardly to say that? Not 2x, not x plus x, x times x. It goes as x squared. Okay? I think I saw you in the chat, recognized. And so the way I can simplify this equilibrium expression down is by writing that reactant in the denominator squared. In other words, the coefficient of the reactant goes into a superscript, raised to that power of the denominator's activity. Okay? And this is a pattern in how we write these expressions for these reaction quotients that we're going to use ultimately to describe equilibrium. Okay? Let me describe a reaction in general. The unbalanced version of this would have some chemical stuff A reacting with some chemical stuff B to form some chemical stuff Y plus some chemical stuff Z. The balance of this thing, however it gets done, puts superscripts in front of each of these guys. And these superscripts are represented by little a, little b, little y, and little z. If I know that this is the nature of the reaction going, the reaction quotient for this reaction will be the activities of the products raised to the power of their stoichiometric coefficients divided by the activities of the reactants raised to their stoichiometric coefficients. And this example is presented primarily to help us set a pattern of every time we go through and look at a chemical reaction of this sort, when we write down this reaction quotient, we're looking for the superscripts in the coefficients of each reactant and product present. We've got our one example that set the stage. We've got the general case. Let's go through a number of different examples and make sure we recognize the pattern in play here for the writing of these reaction quotients. Okay? Classic first example. Carbon monoxide reacts with hydrogen gas to form methanol. And there's a pattern in how you write these reaction quotients that follows the chemical equation. First thing you ask is, hey, what's my product? Because my product is going in the numerator. What's my product in this reaction? Next thing you ask is, what's the coefficient in front of my product? Well, there is none. And when there's no coefficient in front of the product, the implied coefficient there is what number? 1. And so I'm going to raise everything here to the first power, which is like raising it to no power at all. Just leave it. And then what are the identity of my products? Because they're going on the denominator. What's the coefficient of CO? It's the implied 1 again. And I write down my H2. What's the coefficient on H2? 2. That guy's getting squared. And that starts to set the pattern for how we're going to write these reaction quotients down. Now, you might run into a problem in the homework that says write down the equilibrium constant expression instead. Well, that's the same thing. The reaction quotient and the equilibrium constant are not expressly the same thing, but the way you write down their expressions are exactly the same. Just I'm using reaction quotient in my language here because the reaction quotient is the general case. Anytime I have concentrations of CH3OH, CO2, and H2, CO and H2, excuse me, in hand, I know that anytime I have those concentrations in hand, I know that the reaction quotient is going to be the concentration of CH3OH divided by the concentration of CO divided by the concentration of H2 squared. If it happens to be an equilibrium constant, then I happen to be at the exact right conditions for equilibrium. Again, we'll address that more later. Okay, let's work out another example along these lines. Formation of ammonia gas from its elements. Classic example. What's my products? Got NH3 as products. What's the coefficient in front of NH3? 2. Better square it. What's my reactants? Coefficient in front of N2? Not implied. Am I done with my reactants? What else? Coefficient. Cubit. The reason this is such a canonical example is because of that cube in there. It's also the reason why this particular equilibrium is such a bear to solve for, because you have to solve a cubic in order to get there. And solving cubics is nobody's algebraic idea of a fun time. I don't care how much algebra you've gotten. Okay? You see the pattern emerging? Try the pattern on your own terms. Try to dialogue this through with yourself. Okay? Combustion of methane. CH4 gas plus 2 O2 gas. Back and forth 2. CO2 gas plus 2H2O gas. Write it down in your own terms. I'll give you a minute. Oh. Sorry about that, people on Zoom. I tried to clear something out and I did clear too much out. How'd you do? If you got it, do you see the pattern? If you missed it, do you see the elements in the pattern that you missed? Remember that because there are coefficients of 2 in front of the H2O and 2 in front of the O2, somebody should be yelling at me right now. Yeah, I've completely flipped that over when I was writing it down. Reaction quotients are products over reactants. This is your classic example to remember to never trust the professor. I don't care how much of a PhD he claims he has. Professors mess up as well. Let's try writing this again the right way. I did 2 examples perfectly. The example on freeform, I completely botched. Now do you see the patterns in hand? I have no trouble ever telling on myself by making a mistake like that if it A, impresses on you to trust yourself, and B, impresses on you that the professor can make mistakes too. Before I go forward, have a look at these reactions that we've been talking about here. What do all these reactions have in common? What they have in common is the thing they have in common as well with the very first example we launched into, where we had nitrogen dioxide gas combine with itself to form dinitrogen tetroxide gas. What does that story have in common with every story I've got up here right now? With every substance I've got up here right now. Every blasted thing is a gas phase story. Okay? Physical chemists like gas phase stories. We like these stories a lot. We like these stories because the gas particles are dispersed and very active, and we don't have any points of confusion about their activity. We like them even when we're expressing their activity in terms of concentrations, in terms of moles per liter, instead of expressing them in terms of pressure. Okay? Is everything in real life going to be in the gas phase? Probably not. And I need to make sure I know how to deal with other phases as well. Now, one other story I could tell very quickly. I could tell a quick story about something in the aqueous phase. Aqueous phase is a phase I'm used to using concentrations, right? So we can tell a story about the aqueous phase real quick. I actually wrote this out last hour as a quick and dirty example of the aqueous phase, and you went, you know what, this is a very bad example. Why is this such a bad example? Why does sodium chloride dissolve in water in the first place? What's the big thing that drives sodium chloride dissolving in water? It's up there.
They cancel out.
Don't think about canceling out in this case. I see what you're saying. The charges do cancel out, but think about what's going on with the sodium chloride structure when water gets in contact with it. It busts up into ions. The thing that drives sodium chloride dissolving in water is the fact that it doesn't want to be sodium chloride together anymore. It wants to be sodium ions and chloride ions surrounded by water, separated out. Okay? And I can totally write down a reaction quotient for this. It's a fairly easy reaction quotient to write. Products, all with one coefficient in front of them, over reactant dissolved in water. But NaCl isn't going to be very abundant in the aqueous phase when it's together. What's really going to be abundant is the Na plus ions and the Cl minus ions. So even absent equilibrium conditions, we're probably going to find that this quotient is something like 10 to the 10, 10 to the 11, 10 to the 12. When we hit equilibrium, it might be even higher than that. Really comically large numbers for this quotient. Okay? Things I can write down concentrations for easily are the things we tend to represent in these reaction quotient expressions. Gas phase and aqueous phase are the things we tend to write down. Well, what do gas phase and aqueous phase have in common? They're what we describe in chemistry as dispersed phases. So a lot of what we've been describing here is dispersed phase chemistry. Gas phase chemistry is dispersed phase chemistry. Aqueous chemistry is dispersed phase chemistry. What do you think the opposite of dispersed phase is? What do you think is the other side of a chemistry where stuff is spread out and separated from one another? I got a really good answer last hour in one word.
What was the question?
What's the distinction? What's this opposite of a dispersed phase chemistry? And I just got an answer in the room of solid phase chemistry. And solid is as good as we can do for a single word answer, right? But it's not a complete answer, as it turns out. Obviously, solid particles are really smashed up right against one another, not moving around a great deal. But there are also other phases. Well, there's one other phase substantially where the particles in that phase are strongly attracted to one another by intermolecular forces. And they hold on to one another. The liquid phase is every bit as much of its opposite of a dispersed phase as solid phases. Now, aqueous phase is something where I've got things like sodium ions and chloride ions surrounded by water, and the sodium and chloride ions are spread out in a ton of water. The water is condensed together, and the water then disperses the sodium and the chloride ions. Okay, so the aqueous phase of a solution we consider to be dispersed. And the solid and liquid phases we consider to be condensed. And so whenever we actually study condensed phases in a chemical equilibrium like this, we effectively don't count their activity in the expression. We effectively say that the activity of those condensed phases is 1. So all of the equilibria that we've been talking about to this point, all of the chemical reactions we've been talking about are homogeneous equilibria. A homogeneous equilibrium is a chemical equilibrium, singular, chemical equilibrium where all of the molecules are in a single dispersed phase. Usually gas or aqueous. But in this course, all the time gas and aqueous. Those are the only 2 examples of dispersed phases I have addressed at all. And so what would the opposite of homogeneous equilibrium be? If not homo, then hetero. I never know whether to pronounce it heterogeneous or heterogeneous or what have you. The typical heterogeneous equilibrium is an equilibrium where molecules are in one dispersed phase and one condensed phase. And the way you write down equilibrium constants and reaction quotients for heterogeneous equilibrium is you write down everything that's in the dispersed phase and nothing that's in the condensed phase. Let's start talking through an example of that. I got this from the Libre text. standard textbook introduction to chemical equilibrium. I looked at this after the fact and went, you know what, this is a really lousy example because carbon dioxide is very rarely, if ever, going to spontaneously decompose into gaseous oxygen and solid carbon. I suppose I can burn carbon in oxygen to make carbon dioxide, but that does tend to want to go one way. Nonetheless, it's a good example for these purposes. What's in my numerator? What's the product? CO2. I'll do a concentration story again. What's in the denominator? What are my reactants? One of those reactants is in a condensed phase and I don't count it. Which one? The carbon. And so I only put in the denominator the O2. Because the carbon is in a condensed phase and its activity goes as 1. Personal favorite example of such an equilibrium is the oxygen generator potassium chlorate. Potassium chlorate, when it goes through a decomposition, will break down into potassium chloride and then into oxygen gas. Okay? What are my products? I'm now in the part of the program where people are still writing down products. What are the products? Oxygen. For some funny reason, you didn't say KCl. It's a product, but it's a solid. It's in a condensed phase. What's coefficient in front of oxygen? Better cube it. Where are my dispersed phase reactants? Oh, that's right. I have none. I'm done here. This doesn't tend to be the most useful reaction quotient ever because it doesn't actually describe a whole lot. Some reaction quotients are more useful than other reaction quotients in telling stories like this. Let me talk about an especially useful couple of reaction quotients. And let me go ahead and expressly write these as equilibrium constants because of how you're going to see them turn up later in the course. And again, like I said, in the homework, you'll frequently see these things. You're asked to write them as equilibrium constants. You'll write them in the same way. People from my Gen Chem 1, you remember lead to iodide, right? Remember that story that we did for solubility in the first course where I had the demonstration video of the two clear liquids coming together and generating that really stark yellow solid? That yellow solid is PbI2. It doesn't tend to dissolve in water that much. But when it dissolves in water, it gives up lead-2 ions and iodide ions. Now, even though I'm writing this as an equilibrium, it goes the same exact way as any reaction quotient we've written thus far. What are my products? What are my dispersed phase products? Got the PB2 plus. What's the coefficient in front of PB2 plus? Not terribly bothered about a 1 coefficient. And the other is what's the coefficient in front of I minus? So I better square him. And because I've not written much room for a denominator here, you can take a wild harebrained guess what my dispersed phase reactants are. Once again, hey, that's right, there are. This very special equilibrium constant is known as a solubility product constant. It's equilibria of this sort that are going to wind up helping us determine the solubilities of particularly comparatively insoluble compounds. And so we'll get a little bit later into the course, and we're going to have more to say about equilibrium like this, where we have one solid phase reactant and we have ionic products. Okay? Let me give you one more to have you thinking on your feet a little bit. See if you can write down the accurate equilibrium constant expression for this reaction right here. Now, in the aqueous phase, HF is known as what? Gen Chem 1 nomenclature reminder, what's HF in the aqueous phase? If it was in the gas phase, it'd be hydrogen fluoride. But in the aqueous phase, it's what? It's hydrofluoric acid. So this is a reaction of an acid in aqueous phase with water to form a couple of new ions. And write down an equilibrium constant expression for this. Identify the matter in the dispersed phase. And identify the matter in the condensed phase. And only use the matter in the dispersed phase to write down the ratio. And you know what? If I'm really good this time, I'll remember to do products over reactants. This type of equilibrium constant is known as an acid dissociation constant because it represents the tendency of the acid, hydrofluoric acid, to break up into ions in combination with water. Water's the condensed phase reactant here. Water doesn't appear in the expression at all. Everybody else does. We see the pattern. Okay, the examples help. Okay, I did my best to choose these examples to try to avoid the examples in the homework that'll help you get more practice. But by all means, do the stuff that's in the homework. Now, let me tell you one other thing about the way that this chapter is set up. Okay, most of the chapters, if you've done the reading of the textbook, have a very gentle, very polite conceptual introduction to the material in the chapter, kind of easing you into the chapter before you start to dig deep. Okay, chapter 13 of your textbook is not that gentle. Chapter 13 of your textbook dives in immediately into a mathematical expression. And the mathematical expression that chapter 13 dives into immediately is a relationship between the Gibbs energy for the reaction and the equilibrium constant of the same reaction. That relationship looks like this. Remember me talking about the natural log when we did entropy a couple weeks back? Okay, natural log is going to start to figure prominently in work that we're doing. Make sure you're comfortable with the natural log. Okay, just in the interest of time saving, I'm not going to do the algebraic demonstration of how I get to the equation here, solve for K. But this equation is every bit as important. And I want you to be aware of it. And the value of R is even more important than that. Now, R is the ideal gas constant. And R's value you've used in a lot of mathematics, yes? 0.082058, right? We're not using that R here because that's in liter atmospheres per mole per Kelvin. So I'm just going to do this little bit of writing down here. So I can take this and line through it for our purposes here. And then write down the value of R in joules per mole per Kelvin. And that's the value of R we're going to be using in these stories. But this relationship is important because if we know a standard free energy for a chemical reaction, we can get that reaction's equilibrium constant and vice versa. If we know the equilibrium constant, we can get a standard free energy. So let's go back to our very first example one more time today. And let me provide once more time that standard free energy. negative 2.8 kilojoules per mole. Let's compute an equilibrium constant from this. Now, this is in kilojoules, this is in joules. When I've got two units running around like this and I'm in doubt, what do I need to do? I better convert somebody. Who needs to get converted? Energy needs to get converted from kilojoules per mole to joules per mole. How do I do that? Not divide, you multiply. Okay? Make sure you have that distinction down, because that's going to come back in a lot of these problems over and over again. What temperature did I say this standard energy was at? Yeah, most of these guys that are standards are at 298 Kelvin. So I use that as the temperature down here. Negative of a negative is a positive. 2,800 divided by 8.314 divided by 298 gets me 1.13. And E raised to the 1.13 power is going to be equal to 3.10. What in the world does that mean? Well, I know how to write an equilibrium expression for this reaction. And that equilibrium expression, because of that calculation, is going to turn out to be equal to 3.10. That ratio right there of N2O4 to NO2 squared will always be equal to 3.10 at equilibrium at room temperature 25 degrees Celsius. And this is the key that opens me into being able to do things for amounts. If I know how much NO2 I got in this container, what concentration in moles per liter, I can find out what concentration I have of N2O4 in moles per liter. Okay? Is it obvious from this much just how mathematical we're about to get? Okay. Once again, this is the point where I really emphasize getting on the homework's gonna help you large. If you've been off the homework, the chapter 13 homework is a good place to start so you can write down these tendencies that we have in how we're expressing these equilibrium constant expressions, these reaction quotient expressions. Over the course of the next couple of weeks, especially, we're going to get into working through problems with these guys. And these problems are going to be multi-step and heavily mathematical, and problems where I'm going to want you to have a core of understanding in place. Okay, so get ahead of that game now for in anticipation of the work we're going to do. Particularly when we start talking about equilibrium acid-base situations, that's stuff that comes back to see you when you go into organic, when you go into biochem, when you go into an environmental study. pH and acid-base stuff is one of the major reasons that many of you are taking Gen Chem 2. And so what we're doing in the next couple of weeks is really important for building that understanding. I hope you take it as seriously as I'm presenting. Okay? And with that note of encouragement, I'll be done for today.